Hi, this is Alfozia Nihar from At Home Tuition. Welcome to our session today. The topic that we are going to discuss in our today's video is substitution rule for indefinite integrals. Please look at the formula. Let g be a differentiable function and suppose that f is an antiderivative of f, then you can look into this formula. So this is the formula, this is the substitution rule that we are going to use for indefinite integrals. A natural question at this stage is how to identify the correct substitution. The answer is it depends on the integral, unfortunately. However, there is a general rule of thumb that will work for many of the integrals that we are going to be running across. When faced with an integral, we will ask ourselves what we know how to integrate. With the integral, this formula, we can quickly recognize that we know how to integrate. Let me take one example and explain you. Please look at this question. However, we didn't have just the root, we also had stuff in front of the root, and more importantly in this case, the stuff under the root. Since we can only integrate roots if there is just an x under the root, a good first guess for the substitution is then to make u be the stuff under the root. Another way to think of this is to ask yourself, if you were to differentiate the integrand, we are not, of course, but just what a second pretend that we are. Is there a chain rule, and what is inside the function for the chain rule? If there is a chain rule for a derivative, then there is a pretty good chance that the inside function will be the substitution that will allow us to do the integral. We will have to be careful, however. There are times when using this general rule, the formula that I just displayed, can get us into trouble or overly complicate the problem. We will eventually see problems where there are more than one inside function or integrals, it may be one or more, that will look very similar and yet use completely different substitutions. The reality is that the only way to really learn how to do substitutions is to just work lots of problems, and eventually you'll start to get a feel for how these work, and you will find it easier and easier to identify the proper substitutions. Now, with that out of the way, we should ask the following question. How do we know if we got the correct substitution? Well, upon computing the differential and actually performing the substitution, every x in the integral, including the x in the dx, must disappear in the substitution process. And the only letters left should be u's, including a du, and we should be left with an integral that we can do. If there is a x left over or we have an integral that cannot be evaluated, then there is a pretty good chance that we chose the wrong substitution. However, there is at least one case, we will be seeing an example on this, where the correct substitution will actually leave some x and we will need to do a little more work to get into the work. Again, it cannot be stressed enough at this point that the only way to really learn how to do substitutions is to just work lots of problems. There are lots of different kinds of problems, and after working many problems, you will start to get a real feel for these problems. And after you work enough of them, you will reach the point where you will be able to do simple substitutions in your head without having to actually write anything down. As a final note, we should point out that often, in fact in almost every case, the differential will not appear exactly in the integrand as it did in the previous example. This is the example. And sometimes we will need to do some manipulation of the integrand or the differential to get all the x to disappear in the substitution. Let's work some examples so we can get a better idea on how to do substitution rule works. Here is an example. Please look at the question. In this case, it looks like we have a cosine within an inside function. And so let's use the substitution. Let u equal to w minus ln w. So what would be the du? So du is going to be 1 minus 1 over w times dw. So as with the first example, we work the stuff in front of the cosine appears exactly in the differential. The integral is then, you can just rewrite this as integral cos of u, this entire thing is going to be du. So the integration would become sin u plus c. Please don't forget to back substitute the u that you assumed initially. So you have to do the substitution. So your answer would become sin of w minus ln w plus c. So please don't forget to go back to the original variable in the problem. Okay, hope you're clear with this example. Let me take a little bit trickier one. Here is the next example. Please read the question carefully. Again, it looks like we have an exponential function within an inside function. That is the exponent. And it looks like the substitution should be u equal to 4y square minus y. Also, you have to find the du. So, du is going to be 8y minus y minus 1 dy. Now, with the exception of the 3, the stuff in front of the exponential appears exactly the differential. Recall, however, that we can factor the 3 out of the integral. And so, it won't cause any problems. The integral is then. This can be written as 3, you can take the number outside, the constant outside. And this would become e raised to u, and rest of the expression would become du. Am I right? So, derivative. This integration of eu du will become 3 e raised to u plus c. Again, back substitute the u that you assumed initially. So, the final answer would be 3 e raised to 4 y square minus y plus c. That's it for this example. Okay, let me take one more and explain you. Here is the next example. In this case, it looks like the following should be the substitution. I mean, this one. U would be 3 minus 10x cube. So, what would be du? This would become negative 30x square dx. Hope you are clear with this step? Okay. Now, we have a small problem. We have got an x square out in front of the parenthesis. But, we don't have a negative 30. This is not really the problem. It might appear to be at first. We will simply rewrite the differential as follows. X square dx can be written as, if you divide both the sides by 30, negative 30, then it would become negative 1 over 30 du. With this, we can now substitute the x square dx away. In the process, we will pick up a constant, but that is not a problem since it can always be factored out of the integral. We can now do the integral. This would become u raised to 4, and this is nothing but negative 1 over 30 du. Take the constant out and find this one. So this would become u raised to 5 over 5 plus c. 30 times 5 is 150, and if you substitute back this u, you will get 1 over 150 times 3 minus 10x cube raised to 5. Note that in most problems, when we pick up a constant as we did in this example, we will generally factor it out of the integral in the same step that we substitute in. Hope you're clear with these 3 examples. Okay, now I'd like to take an example with a fraction model with a square root. Here is the next example. In this example, don't forget to bring the root up to the numerator and change it into fractional exponent form. Upon doing this, we can see that the substitution is, you can take this innermost function as u. So du would be negative 8x dx. We just need an expression for x dx. So you can divide both the sides by negative 8. So this integral can be written as, now using these substitutions, you will get negative 1 over 8. As that is a constant, you can take that out. So this would become negative 1 over 4 u raised to positive 1 over t, 1 over 2 plus c. Please make sure that you substitute back the u value that you assumed initially in the problem. That's it for this example. Hope you're clear with this one. So in the 4 set of examples, the substitution was generally pretty clear. There was exactly one term that had an inside function, and so there was not really much in the way of options for the substitution. Let's take a look at some more complicated problems to make sure that we don't come to expect all substitutions are like those in the previous set of examples, what we just discussed. So in the next set of example, we will learn the most important thing to remember in substitution problems is that after the substitution, all the original variables needs to disappear from the integral. After the substitution, the only variables that should be present in the integral should be the new variable from the substitution. Generally, we use u. Note as well that this includes the variable in the differential. So let's put the rest of the substitution rule examples in the next video. With all the examples was becoming too large for this video. So this is all about the initial introduction and introductory examples for the substitution for indefinite integrals. In our next video, we are going to discuss the more complicated examples with two sets of example sets. Hope you're clear with all the topics that we discussed in our today's video. In case if you get any query, please let me know.